So let's talk about section 5.1, exponential functions. Now, with exponential functions, this does lead into a new function that we haven't talked about yet, but don't forget everything that we've learned previously. So we're gonna talk about graphing and applying exponential functions, but we are also going to talk about finding some asymptotes, some horizontal asymptotes, and we're going to look at applying graphing and applying exponential growth and decay functions and being able to compare them with transformations. So because we are talking about transformations, that does mean that we need to remember the rules for functions with transformations. So remind yourself that you've got this base function that we're talking about. And again, if I add or subtract to the base idea of it, we're going to move it up or down. And again, all that does is move the x or y coordinate itself. Also keep in mind that if we are doing plus or minus some number inside the function, so this will be inside wherever x is, it's attached there. It's normally inside a set of grouping symbols or in some grouping area there. That's going to be that horizontal movement, which again is going to only affect the x value there. If you're multiplying by a negative on the outside of the whole function, or if you're multiplying by a negative on the inside of the function where there's next to x itself, that's going to be those reflections. And then we have the vertical stretch and shrink and the horizontal stretch and shrink. Okay, so all of this stuff that you've learned previously is still going to show up when you talk about exponential functions. So let's just start right in with a word problem here. So we have a primitive single cell animal called a Parsimium, and it reproduces by splitting into two pieces. So basically the population doubles each time there's a split. So the number y, we'll call it just y itself, of Parsimium in the population after x hours have passed fits the graph of y equals 2 to the power of x. Now, in the context of this application, what inputs can be used? Now, do remember that this is y equals 2 to the power of x, so that x is actually an exponent here. And this is the first time that we've actually dealt with x being an exponent. Now, we are talking about x being the number of hours. So if you think about it in terms of number of hours, there's going to start off with 0 hours because I don't have negative hours. We don't ever talk about, well, you're going to be negative 2 hours. No, we talk about hours as like 0, 1, 2, 3, 4. So that kind of is going to basically be those inputs for which could be possibly used for those x values there. Okay. But for example, when we look at that, that does not necessarily mean that my answer is going to be a whole number every single time. Now, I did say we could basically plug in inputs like 1 hour, 2 hour, 3 hours, but remind yourself that you could have basically like an hour and a half, which would be 1.5. Since whole number inputs will give pretty much our whole number outputs, the whole number inputs would basically be the only idea for the application because this is a word problem. The reason why I say that is that if we plug in 2 hours, 2 to the power of 2 is going to be 4, whereas if I plug in, say, 7.1, there's nothing stopping me from plugging in 7.1, but the output is going to come out to be this kind of really weird decimal, and it doesn't actually represent a cell. Like that's not a whole cell. It's like in the process of doing something. And so we would kind of limit it to basically inputting whole numbers, meaning basically no decimals, because it's a word problem. So in that sense there, we call this discrete or continuous. So y equals 2 to the power of x. Well, every point describing a number on the graph means that the function itself is continuous. Okay, so when we graph this, just this part, not knowing anything about what x and y are, the function itself is continuous. However, when we are talking about it in terms of the items that we are looking at, so remember, x is the number of hours, but the output is how many of these cell items, the paramecium. So in those cases there, because we're talking about that, paramecium being a cell, those are discrete because you can count those. We don't have like 0.1 of one. We literally, you have a whole cell or you don't have a cell. So that's kind of where you want to look at that, and we want to take that into account. So if we disregard the restrictions of this being an application problem and just look at it as the function y equals 2 to the power of x, let's look at it with all the different variables that I could plug in. So if I don't think about it in terms of x being only in hours, but I actually use negative numbers, I could actually plug in -3 and actually get an answer back out for that x value. So if x equals -3, that means I have 2 to the -3rd power, which is 0.125, also known as 1/8. Okay, and we can look at that looking at a bunch of different numbers there. Okay, you'll notice that on some of these ones, especially the ones that have decimals, it's because we have a decimal input number, so it's not an exact number. It didn't land perfectly whole. Okay, but what I do notice is that all of these y values happen to be numbers that are positive. There's no negative value here at all. I'm plugging in negative numbers, but I'm not getting any negative numbers back out. And that's actually really cool to see. So let's actually graph all these and put them together. So here's some of all of it put together in a table format, but sometimes looking at the graph makes it really cool. So as we can see on that graph, we can see that if I were to graph a ton of points, this is kind of the shape that it makes. And one of the things I want you to notice is right down here at this part. So as I'm looking at this part here, you'll notice that it's getting close to basically y equals 0 here, but it doesn't actually hit y equals 0. You'll notice it's not actually crossing the line. It's kind of looks like it's kind of heading to the point where it's going to lay down on the line. And that's really important to make note of. Okay, so what is the domain and range of just the function, not the word problem, just the function, y equals 2 to the power of x? Let's go back to this picture one more time. Domain. Now remember when we talked about domain, remember for the keywords there, domain is my input. In our case here, my input is x. So we're looking for our domain, which is basically what we most of the time think about as x values. And then our range, which again, most of the time we think of those as our y values. Again, it's not necessarily x and y, it's just that's what we use majority of the time for our input and output. So if we take a look at this graph, maybe look at it from left to right, that might help us a little bit here. So as I go to the left, this graph looks like it kind of continuously goes left forever. And as I go to the right, again, even though this is moving up, it's moving up and slightly to the right. It's a little bit slower in moving to the right here, but it is moving. So it looks like my domain looks like it can be pretty much anything. Okay. Now for the range, we always start down to up. Now, one of the things I notice is if I keep going in this direction here, it is kind of, like I said, it looks like it's kind of like really slowly bottoming out. It doesn't look like it actually is going to cross this. It looks like it's kind of making that curve, like it's going to skim next to it. So it doesn't look like I'm going to have any negative values there. And we were kind of seeing that when we were plugging in numbers, but I do see that this kind of goes up forever in that direction. So when we talk about the domain of this one here, the domain is not restricted at all. The domain happens to be all real numbers, but the range is restricted. Okay. One of the things you want to note about the range on this one is it's only positive numbers. So those y values we keep getting back out will only be positive. And if you really think about really closely about it, 2 to a power, there's pretty much no way to ever get a value of 0 there. Okay, so this whole idea of 2 to the power of x is actually what we refer to as an exponential function. Okay, now with our exponential functions, we do have a couple of rules. So if you want to think of it as basically f of x equals b to the power of x, you can also say y equals a to the power of x, whatever. There's a bunch of different ways, but there are a couple of rules here. In this book here, we actually like to use b. And the reason why we actually like to use b a little bit more than a is b for base. Okay. And we'll see it later show up with b as well. So again, just remember b for base. Now the base of our exponent, so that's why b for base here, is got a rule. Okay. B is basically going to always be positive. Okay. But The other rule is b is not allowed to be 1. Now, there's a reason why we won't let it be 1. And think about it. If you really actually think about it, it makes sense. So what's 1 squared? 1. What's 1 to the 3rd? 1. What's 1 to the 5th? 1. 1 to the 7th? 1. 1 to the 51st? 1. So even if I plug in anything up here for x, like even if I make this -2, it's still positive 1. Make it -3, it's still positive 1. No matter what I raise the power of 1 to, I'm always going to get 1 back. So it just kind of makes sense to kind of ignore that, okay? And so that's why we don't let the base be 1. But it can be anything else that's positive. Now, we're not going to let it be negative because, one, that's going to lead into a higher level math than this class is actually prepared to go into. So that's the first reason. Second reason, that takes us into basically a whole nother number system, which again is why we say it's a whole different level of math, and we're just not going to go there. So our rules is that base is always going to be positive and just not 1 itself. Now, anytime you take a look at these beautiful exponential functions here, one of the things that you will notice is that if we have this b to the power of x, we do have that transformation possibility to happen there. If I throw a negative in front of that x, again, the negative is in front of the x value. It's a negative that's being multiplied. That is what we have is a reflection. Now, it reflects, you'll notice here's the graph here. And again, I'm going to kind of go into my pointer mode here. This graph is our normal base graph. But if I put a negative in front of that x, it's going to literally reflect the graph about the y-axis, okay? And again, that's if that's negative in front of that variable that is an exponent there. That's why it becomes a reflection on the y-axis there. But the graph still looks very similar, so it really just kind of depends on if there's a negative in the exponent or not. So if the exponent is negative, we end up with this kind of decreasing function. And if the exponent is positive, we have an increasing function. But what's really important to know on both of these functions is this one point right here. This point is the y-intercept, which is 0, 1. This is going to be the point that you want to watch. And that's the one that you can kind of see most of the transformations on. Okay. So let's take this function y equals 2 to the power of x minus 3, and let's see if we can maybe describe the transformations on it. So the first thing you want to do is remind yourself, kind of cover up that -3, and if you cover up any number that's being added, subtracted, multiplied, or divided, you can kind of look for that base idea here. So my base function is going to be y equals 2 to the power of x. And in y sub 2, go ahead and plug in y equals 2 to the power of x minus 3 and see how that transforms. Okay, so hopefully you graph them. And when you graph them on the same graph, one of the things, again, remember I said, look at this point right here. This black line is going to be that y equals 2 to the power of x. But when I look at that y equals 2 to the power of x minus 3, which is my blue line here, this point here, again, the -3 is inside with the x. So anything inside is going to be kind of a horizontal style movement here. And it's being subtracted. So that means we are going to be moving to the right 3 places, and notice where that point ended up. Okay. So the graph looks exactly the same. It's just been shifted to the right. So what if I say, take that 2 to the power of x minus 3, but now I'm going to add 3 outside here. Now, again, we already know that this -3 inside here is going to shift that graph to the right 3. But what does this +3? Again, this 2 here is just the base. That helps me with the shape of the graph. So the graph will still have the same shape here and here. But we know that we're shifting it to the right 3. But that +3 out here actually takes that graph and shifts it up. Now, remember I said that it looks like it doesn't actually touch the y-axis. Sorry, excuse me. It doesn't touch the x-axis. It's like it just kind of lays down here, but never actually touches it. It just gets super, super close. That is what we call a horizontal asymptote. So the horizontal asymptote is here. However, when I took that graph and shifted it to the right 3 and then shifted it up 3, that horizontal asymptote is still there. It's just now been moved up to y equals 3 itself. Okay. Well, what if I have it as 4 times 2 to the power of x? Again, think back to those transformations. Now, this 4 is what's so different between 2 to the power of x and 4 times 2 to the power of x. Again, this 2 has nothing to do with any transformations. It is to deal with the base shape of the graph. But this 4 is being multiplied. So anytime we talk about multiplication of items, and again, it's a positive 4, we are looking at basically a horizontal or vertical stretch or shrink. Okay. Now, how do I know if it's a horizontal versus vertical? That 4 is on the outside of the shape of the graph, which again, when I say outside versus inside, if it was inside, it would be attached to the x up here. So it would say like 4x, but this is 4 times the whole function. So that right there tells me it's vertical. And anything that's vertical is kind of exactly what we think it is. So 4 looks big, so I'm going to say it stretches by a factor of 4. Okay. Which means that basically that point that I said for you to watch, that y-intercept on the original graph, y equals 2 to the power of x, has been basically multiplied up by 4. So instead of it being 1, it's now 4 for the y value. Okay. Now, these types of exponential functions that we're looking at have also been given another name. They are sometimes called what we call an exponential growth model. Okay. Now, they look very similar. The biggest difference between these and what we were originally looking at is previously we were looking at the very, very base part of the function. So that y equals b to the power of x there. However, when we look at it in terms of a growth function, the growth function is going to have a lot more added to it. Okay, so we're going to end up with this y equals a times b to the power of k times x. Now this a itself is going to be that whole vertical stretch or shrink. Again, it's going to depend on the number here. K itself would be that horizontal stretch or shrink. Now, again, if it goes negative, if a or b go negative, sorry, not a or b, a or k go negative, then that means we're dealing with reflections, okay? But for the most part, we're going to just look at it, because I'm using the word growth here, we're going to say that k is positive. Okay, so let's kind of look at this and see how they end up coming about. So suppose that inflation is predicted to average 4% per year for each year from 2012 to 2025. Now, this means that an item that costs $10,000 one year will actually cost 10,000 times 1.04 the next year. Now, again, where did I get this part right here? You're probably asking. Well, I'm going to have 100% of my money back. So that's where the 1 comes, plus that 4%. So 100% plus 4% is 104%, which when you change that to a decimal is 1.04. Okay. And the next year after that, it's going to be that same amount that we had from the previous year times another 1.04%. Now, because this and this look identical, we could possibly rewrite that as basically 1.04 quantity squared. So what if I keep doing this? So this was basically after 2 years. So this was my first year. This was my second year. What if I keep doing? Well, what's that pattern going to look like? So again, I'm starting with an item that costs $10,000, and then it's got that 4% each year. So that's going to create this kind of new function that we call basically the base amount, which is $10,000, times 1.04, which is how much money plus our increase, our inflation, raised to the power of t. Now, t is going to be for any year. So if I do 2 years, so if we say t equals 2 years, that would literally be what we have up there with that 1.04 to the power of 2. That would be the t equals 2 years. If I say t equals, say, 5 years, again, it's going to look very, very similar, but instead of saying 1.04 to the second power, it's just going to say to the 5th power. Okay. So now that we've got that, let's actually graph that model found from part A for t equals 0 and t equals 13. Okay. So again, our part A function was this 10,000 times 1.04 to the power of t. And I want to do it for t equals 0. So that means I need to plug in 0 here and then 13. Now be very cautious of plugging in 0, because that does not mean that you're multiplying by 0. You're raising it to the power of 0, which changes it. Okay. Now, as I graph those all the way there, so let me erase that. You can kind of see, again, it does have that bit of the curve. And again, at t equals 0, where does it start? It actually starts at that 10,000. Okay. So when I plug in that 10,000 times 1.04 to the 0 power, again, remind yourself that's basically going to be 10,000 times 1, because anything to the 0 power is 1, not 0, which is why we get 10,000. So if I start basically with my item at 10,000 and no time has passed, I still have $10,000. But over time, each year, the inflation of the item goes up and up and up and up, and we can see that it's steady growing. And again, it's got that kind of, it's got a very small curve. Okay, so if an item actually costs $10,000 in 2012, use the model to predict the cost in 2025. Okay, so we're going to use the model. Now, again, we just figured out our model was basically this function that we created at the very beginning with that power of t. Now, remember, t is going to be the number of years since 2012. So this is basically time t equals 0. So what is t equal for 2025? Well, if you said 13, you're correct, because 2025 is 13 years later than 2012. And now all we have to do is plug it in. Now, be a little cautious on any type of problem. See what is it asking to round to. If it asks you to round to the nearest whole number, then you'll round to the whole number. If it's money, majority of the time it does ask you to round to 2 decimal places for US money. Okay. Okay, so let's try this again, but this time let me go ahead and give you the formula. Let's not create it. So the total personal income in the United States in billions of dollars is selected for selective years from 1960 and projected to 2018 can be by the following model. Again, if you have a model, guys, do remind yourself that's very important to make note of. Okay, so we've got this model. And again, first thing I see right after it that is very important for me to keep in mind, X is equal to the number of years after 1960. Okay. So what does the model predict the total US personal income to be in 2014? So 2014 is a year, which means I need to figure out how does that translate in terms of X being the number of years after 1960. And once we figure that out, we can move on to B. Okay, so the first thing I need to do is basically find that X is going to be 54. Now remind yourself how you get 54 is you're going to take your 0 year and subtract it out of 2014, and that's going to tell me that I'm 54 years away, because again, remember 0 years 1960, and then all you have to do is plug a 54 here. So literally plug in 54 in for X. Okay, now graphically determine the year, not the year during the model predicts the total US personal income will reach 28.5 trillion. Now, again, I'm going to point out a couple of key things when you're looking at this here. I'm asking for the US personal income to reach 28.5 trillion. That's really important to make note of, because remind yourself that when we were looking at the function, okay, it was y equals, and then you had some stuff, and then the power of x. And I'm kind of ignoring the rest of the stuff for a second, because what we need to focus on is these two variables. Now remember, x is the number of years since 1960. Okay, that was literally what X was. Y is the only other thing I can plug in for. And in this case here, it's asking for the US personal income will reach 28.5 trillion. This was actually the US personal income. Okay, that was actually what Y was. As we read through the problem, it states that, but it's not as obvious. So in this case here, this problem is actually asking for us to basically graph the function. And the reason why we have to graph it is because we don't actually have the correct methods to solve this by hand just yet. So we really only have the intersection. So we're going to graph the model and that 28,500. Now, why did I say 28,500? So just a quick kind of idea here is I use the word trillion here, but when we were talking about why in the problem, I said it was in billions. So you have to take trillions and turn it into billions there. So that's where it's 28,500 billion. Okay. And then we can use the intersection method. So remember the intersection method was second, trace, and then you've got make sure it's on the first curve, second curve, and then your guess. And this is what's going to end up with. Again, this is kind of something we've done previously, so go back to other videos to watch for the intersection method. So let's talk about the exponential decay models. Now, remember when we were talking about earlier, I said that if you plugged a negative in front of that variable x up in the exponent there, it's going to look like it decreases, and that's where that decay comes in. Okay, so if that k value up here is negative, then we've got this decrease model. Okay, it's still going to look very similar to the other model, except for it's decreasing versus increasing. Okay. Now, again, these are very, very similar problems. These are things that actually show up in real life. So it pays to advertise. And it's frequently true that weekly sales will drop rapidly for many products after an advertising campaign ends. Now, this decline in having the sales is actually what we call sales decay. Okay. Now, suppose that the decay in sales of a product is given by the following function. Okay. Again, anytime in a word problem they tell you a function, you're going to have to be like, yes, I need to make sure I have an eye on that function. Now, as I look at that function, the first thing I do notice is it says it's 1,000 times 2 to the power of a negative 0.5x. Okay, and again, x is the number of weeks, after the end of the sales campaign. Okay, so I'm looking at this function and I notice it's exponential. Again, how do I know this is exponential? Well, pretty nicely there. X is in the exponent, so it's exponential. Okay. I also make note of the reason why I highlighted this part here is X is the number of weeks after the end of the sales campaign. Okay, so my first question is, what is the level of sales when the advertising company campaign ends? Well, if we just end it today, that's basically our ground zero, right? That's time zero. Again, X is the number of weeks after it ends that sales campaign. So if I ask you what is the level right as we end it, then that would be times 0. Okay, so all I have to do is plug in 0 and notice I'm going to get 10,000. Now that's actually really good to know where that 10,000 is. Now part B said, okay, well, what would be the sales after 1 week after it ended? Well, again, take that beautiful function, but instead of X being 0, I'm going to plug in 1. So I went from $1,000 to now $707.11. So $707.11. Okay, so use the graphing function again to estimate the sales when they reach 500. Now again, we started with $1,000. So if we are decaying, reaching 500, again, this is kind of that idea that we were talking about earlier. This right here is basically an output value. Okay, estimate the week. That is an input value. Okay, so this is basically asking me for X, and they've given me a Y value. And again, currently we do not know how to solve these by hand. We will by the end of the unit, but as you learn a little bit more about this, you'll learn more. So what we can see here is that basically our S is 500, and we're going to want to graph both of the functions. So we're going to graph S equals 500, and we're going to graph the model, and then find where they intersect by doing that second trace intersection. Be a little cautious with these ones that you're graphing, because you are going to need to make some major adjustments on the windows. So when the sales falls to $500, that was at when X equals 2. And remember, X was the weeks. So basically sales fall to half their original amount after 2 weeks of the campaign ending. So according to the model, will the sales ever fall to zero? Well, this is one of the cool things about this here. The sales actually will never reach zero. And the reason being is because remember that this graph was that exponential decay. And because it was that exponential decay, it kind of had that, what we call an asymptote. And that asymptote happens to be y equals zero. So it actually never reaches it. Now, is that realistic? Well, I mean, we know eventually it probably will hit zero, but that's only when you stop selling something, right? So if you just stop holding that item or selling it, then of course it's going to hit zero. But if I constantly am selling it forever, sales will never actually fully reach zero overall. I'll always have like maybe a half a sale or even like 1/4 of a sale per week. So it's just going to kind of depend on that. So this is why normally when we look at these models, we only look at them for a short period of time. Okay, so let's talk about E. Now, hopefully you guys are familiar with the number E, but in case you're not, you have seen a number very similar to E before. That number would happen to be pi. So if you think about it, you've seen pi before. It's 3.1415 ... It just keeps going and going and going, right? Pi and E are very similar. They're both what we call irrational numbers. Okay, now E is deceptive. Okay, the reason why I say it's deceptive is it's 2.718281828, and I believe the next number is 4. Like it looks like it repeats, but it actually does not. The calculator just runs out of space to show it. So like when it stops here, it just can't show anything else. But in all reality, it does actually continue just like pi does, and it never actually ends up repeating. So because of this one was given a special name. We call it E. It's called Euler's number, so he got to name it. So that's why it's E. Okay, and it's an irrational number just like pi. It shows up so much in math and especially nature that it literally had its own name. Okay, so that is actually going to come around when we start talking about functions and modeling. So let's talk about our first one here, which is compound continuous. Now, if word problems use like words like compound continuous or an exponential growth function, then the formula you might want to use is S equals P times E to the RT. Now, the only things that you're going to plug in here, and I'm going to highlight them just to kind of make sure that we're on the same page, is S, P, R, and T. Please understand that E that you see there, so this E right here, this is, E is the number E. E is that basically 2.71828 ... number, okay? So E is actually there, and it is on your calculator. So take a second and look for the E. Now it's going to look a little bit kind of like a cursive style, a little bit on the E. So it's almost always on there. And if you're looking at your calculator, you're probably going to see it around the ln button. Okay, so the button that says ln, that's normally that E value that you want to look at. And it's got like E to the power of X. So that's the one that you want to look at. Okay, so if $10,000 is invested for 15 years at 12% compounded continuously, what is the future value of the investment? Okay, so we're going to start by writing the formula for the future value in terms of time. But again, how do I know how to even start the formula is this keyword right here. The fact that they even use the word compounded continuously right away lets us know what formula we want to use, okay? So right there, that's letting us know that we need the S equals P times E to the RT, okay? And we start by just basically plugging in. Again, P is the starting value, which we said was $10,000 is invested for 15 years. So there's T, right? Okay. And at a rate of 12%, so that's my R. Now, guys, we never plug in R as the decimal or as the percentage. We always change it to the decimal. And so I can literally just plug in 10,000 times e to the power of 0.12 times 15. And you should get basically what we would say approximately $60,496.47. So if I put $10,000 away right now, invest it for 12 years at a 12% compounded continuously, that's how much money I'll have in my account. So you definitely want to make note of this formula. And again, this is called our compound continuous formula. That's kind of our key word that we're looking at when we're doing these formulas, okay? And go ahead and start, if you guys will, a lovely kind of sheet for all the formulas that are about to come. In the land of exponential functions, there's a lot of formulas that start to come out. And when we see these formulas come out, you want to make sure that you know when to use them, when not to. So kind of find the keyword. Again, this one is kind of our compounded continuously. That's how we kind of know this is a formula. And we'll start to add other formulas that are very similar, not exact, but very, very similar. Okay. And this will help us kind of work our way through those problems.